So in this series of lectures, what we are going to talk about is something called AC analysis. And we distinguish AC analysis from basically everything else we've been doing the previous part of the semester in the sense that all of our power supplies so far have sort of looked like this. They're a constant or sort of fixed source. So if we look at sort of the voltages from these sources over time, they're fixed at, let's say, like 9 volts, 3 volts, 2 volts, whatever it might be. But in AC analysis, what happens is that our sources are no longer fixed. They oscillate, and these sources are best described by sort of, cosine and sine functions. And what these signals may look like, even if they're voltages over time, what these may look like is something more like this. And so the challenge we're going to talk about over the next couple of videos is we've learned all the techniques about how to analyze DC sources. Now we need to learn how circuits can change and behave with AC circuits. To give you a little more detail, what we mean by an AC circuit, so an alternating current circuit, is that this voltage right here from the source is some function of time. So it is no longer constant with time. And often, and probably generally always, these sources look like sine waves. So they look like these nice little waves right there. And when we write out these sources, so our voltage source is going to look like a cosine function with a couple important parameters. So the first important parameter is the amplitude. So the amplitude tells you how large that wave actually is. So over here on this diagram to the right, I've indicated the amplitude of the wave. This second parameter, omega, is the frequency. So frequency is how often the wave oscillates. And frequency is sometimes a little bit more difficult, but it's easier to remember if you consider frequency relative to period. So recall that the period of the wave is the amount of time it takes it to go from one peak to another peak, and period is in terms of t, it is time, and our frequency is 1 over the period. So period is 1 over f, and likewise frequency will be 1 over the period. Our final parameter right here is this phi. This is called our phase delay. So let me sort of write it up here, phase delay. And phase delay is best described in the relative relationship between two different waves. So with phase delay, it's often best to understand this as a relationship between two different waves. So imagine that I have this blue wave to start with, and then within my system there's another signal coming along, and this signal happens to be the red wave. Now these two waves may have the same amplitude, they may have the same frequency, but what we care about here is the amount of time between the peaks of these waves. And that amount of time right there is the phase delay. And so this phase delay has the symbol phi, and that is going to indicate the amount of time, so this is still an indication of time, between those two waves. So kind of bringing this all back together, we have sources now that are oscillating over time. So we have a time function here and a time function here. And the major components of this function are the amplitude, the frequency, and then the phase delay. We've written this function as a voltage function, but it could just as easily well be a current function. So amplitude here is always going to be, at least in this example, in terms of volts. your frequency, an important note on this is that this frequency right here is in terms of radians per second. And so if you remember back to your different units of angles, we have 360 degrees is equal to 2 pi radians. And so often we will talk about frequency in a couple different units. So this omega here is always in terms of radians per second, but we can convert between radians per second and the normal sort of hertz. So this is radians per second, but this is in hertz by this relationship here. And so I will say that in the problems in the books, it does get sort of annoying because we like to talk about signals at 60 hertz or 120 hertz, meaning that they're going to oscillate 60 or 120 times per second. Whereas when we go to do our calculations, and especially our calculations inside of MATLAB, it's always in terms of radians. So I'll provide a video that goes over how to do that in MATLAB, but know that at times we're going to have to flip between these sets of units, and this relationship right here relating radians per second to hertz is going to be really important. Finally, this phi parameter, this phase delay, is again in units of time, so we can assume seconds. But it's a delay. It's that two angles may be off by a certain amount, and that is their phase delay or their phase shift. So this is our summary or sort of waves and AC signals. What we will talk about in the next video is how do we deal with a circuit that if I have, let's make that black, if I have some sort of AC source, like what actually is going to happen when I connect it up to a resistor and a capacitor. We saw in previous videos or in previous lectures that if I charge a capacitor or I discharge a capacitor, we get these nice oscillations. But that was with a constant source getting switched on and off. What we have now is a source that is constantly switching on and off in values and moving in phase, and it's going to change the way we deal with these circuits. But overall, we're going to have to apply the same nodal analysis, mesh analysis, and everything else we've been doing, but our signals are always going to look like this. And it's going to be pretty difficult to work with them in the time domain. So in the next video, we'll talk about something called phasor analysis, which moves us into the frequency domain. So our signals move from being a function of time into something that is a function of frequency. And I will see you all there.